First of all, I feel very glad to come to Jeju Island this time, and the weather is perfect, and I enjoy the trip very much. In addition, I want to thank the organizers for their hospitality and very considerable arrangements. The title of my talk is on descriptions of product of simplices. Products. On descriptions of products of simplices. Simplices. So I think my talk will be very easy. I hope everybody can understand. A simple convex polytope. A simple convex polytope in my talk means the convex hull of a finite many points. Right? The convex hull of finitely many points. Finitely many points in some Euclidean space. So I think of it as a convex subsets of Euclidean space. And a simple means, I think everybody knows, means that at each vertex it only meets, so say that the dimension of the polytope is n, then at each vertex there are only n facets meeting this vertex. Okay, for example, we have this. So I use this to let's say the standard simplex. So we have this, let's say, product of R simplices. So this is an example. And in my talk, so like the title, so the question is how to judge a given simple convex polytope, whether it is combinatorially equivalent to a product of simplices. A combinatorial equivalence just means that there's a bijection between the faces of these two polytopes that preserve the inclusion relations. Or you can say there's bijection between their face lattices that preserves the order. So this is my question. So in my talk, I will discuss how to judge a simple convex polytope in the Euclidean space is equivalent to a product of simplices from three different directions. One is a combinatorial condition. So I will show several combinatorial conditions to judge this. And the second is topological conditions from the viewpoint of toric topology. And the third is the geometrical conditions. Okay. So first it's combinatorial conditions. We know the construction of the dual. Say let Kp to be the boundary of the dual of the polytope. So P star is a dual polytope of P or polar polytope of P. So P star, by definition, actually P star lies in the dual space of the Euclidean space by definition. But we can show it's also a simple polytope. It's a convex polytope, but it's simplicial. And the boundary is just say if the dimension of P is n, then this is an n-1 dimensional simplicial sphere, right? Kp is just simplicial simplicial of dimension p minus 1. Okay, so this is a simplicial sphere. And we have a simple fact that Kp cross Q is the same as Kp. So this is a join of two simplicial complexes. And then from this viewpoint, then we can easily show that Pn Pn is equivalent to a product of simplices if and only if Kpn is simplically isomorphic to the boundary of the join of the boundary of this. So if the so if Kpn is simplically isomorphic to the join of this kind of boundary of simplicial spheres, then Pn is equivalent to a product of simplices. So this here is simplicial isomorphic. Okay, but of course this is obvious and it is quite trivial. And another construction is called double construction. Double construction. So double construction is introduced by I don't know. It's introduced by some people doing algebraic geometry. I don't know. But later I think I learned this. I learned this construction from Yuri Ustinovsky's paper, and because we can so Pn can be embedded into, say suppose Pn has m facets. So suppose it has m facets, then we can embed Pn into. So Pn can be embedded into the positive cone of m-dimensional Euclidean space by some linear map. And suppose I write the linear equations like this, Qi. So Cij and Qi are some real numbers. J equals 1 to minus n, xi greater or equal to 0. So Pn can be, think of the subset of this positive cone in Euclidean space as the image of this linear map, but with coordinates or greater or equal to 0. So this is one way. Another way to write, to think of it as a subset of this space. And the double of P is defined to be the double LP. The double of P can be defined by the equations like this. It's quite similar with similar coefficients, but we just add extra variables. Qi j equals 1 to m minus n, and xi greater than equal to 0, xi prime greater than equal to 0. So we add extra variables, and then we can show that LP is 2m. It is a convex subset of 2m dimensional Euclidean space, and the dimension of LP is m plus n. So this, and it's a simple polytope in this Euclidean space. Yeah, the example. So L delta k is delta 2k plus 1. So this is a major example, I know. And the fact is LP cross Q equals LP cross S LQ. So this is just a Cartesian product of two sets, and the double of this product of two polytopes, simple polytopes, is same as, or is combinatorial equivalent to LP cross LQ. And dually, and the dual. So dually, we can define the double of simplicial complexes. So suppose we have a finite simplicial complex, we can also define what's the meaning of double of that simplicial complex. So suppose K, so let K be a simplicial complex on a set, say M, 1 to M. Then V1, V2, and Vm. Then we can define a new simplicial complex, say Lk. So Lk is a simplicial complex on 2M. So 1, V1, V1 prime, V2, V2 prime, Vm, Vm prime on 2M vertices. And the definition is, because we know a simplicial complex is also defined by non-faces. So we can just define, so what's the meaning of non-faces? So omega 2M is a non-phase. It's a non-phase. It's a minimal. It's a minimal missing phase. It's a minimal missing phase if and only if omega is of the form say a vi1 prime, vik prime. It's like a double of some where V1, Vk is a minimal missing phase of K.
Well, actually, this kind of operation is already known by.
Yeah. I think it's already known a long time ago. But with Tinovsky, I think realized its importance when he try to understand.
Yes, and he call it doubling.
Doubling. Doubling. You have to say it's not double. It's doubling. Yeah. No, I think he mentioned somewhere else.
Really? But this is just an example of M of J, P of J construction, sequence of wedges, and especially Yuri was concentrated.
It's a special case of some more general construction because he realized some connection between a moment-angle complex and the real moment-angle complexes. Yeah. Okay. So there's some easy fact. The fact is, so the doubling of the drawing of two simplicial complex actually is isomorphic to the drawing of their doubling. For example, this is and this example, the doubling of the boundary of simplex is actually isomorphic to the boundary of 2k plus 1 dimensional simplex. So we can and then using this language, because this kind of thing, P and LP somehow determine each other, and L, L is LK. In addition, these two things are really dual to each other. So if you take the boundary of the double of the polytope and takes the boundary, then each is the dual of its the doubling of its boundary, the dual of its boundary. So they're really these two constructions actually do each other. So we can also say Pn is combinatorially equivalent to a product of simplices if and only if Lpn is equivalent to product of this kind of simplices or Kpn, the doubling of its dual simplicial complexes is simplicially isomorphic to the product of the product of these two drawing. Sorry, it's a drawing of these two simplicial complexes. Okay, so the meaning of this and this are different. You see, because this is a simplicial complex, it's a polytope, but I define them both, right? But of course, these things are not really new. And
this direction is also
this one?
No. The direction from the right to the left.
This to this?
Right to the left.
To right to the left. I think it's not difficult because the simplicial. So these are obviously equivalent. And here you see the simplicial complex is defined by its missing faces also, right? And if you know all the missing, the minimum missing faces, then you know what it is.
So if Lk is isomorphic to Lk prime, and K and K is isomorphic to
Yeah. I think they're kind of correspond to each other. Okay. So, but these things are not really new. I mean, it's just another way to say P is is a product of simplices. Okay. But we do have some very non-trivial things next. So the third description is formally I have to say this is a theorem of Wimler, M.E. Wimler 2015. It says Pn is equivalent to a product of simplices if and only if any two-dimensional faces of Pn is either a three-gon or a four-gon. I want to say something about this fact, but actually this fact I first learned this fact from Su Yang because I think he knew this fact probably 6 years ago. So when we are together in Osaka City University, but he has many ideas. He's busy with something else, and he didn't write the proof down. But later, last year, and the formal publication of the proof is due to him. And so this is a very nice. I think this is a very, very nice criteria to judge whether this is product simplices, because you can only just check the two-dimensional faces, whether it's a triangle or a square. So this is quite nice. And also this property can be inherited by all the facets of the polytope, right? Because it says two-dimension. Okay. And actually I also think about the proof of this statement by myself, and during the So during my thinking, actually, I happened to find another criteria. So this is the fourth one, which is due to me. So I already. Okay. So now I'm present the content of a paper of me and Professor Masuda, and you can already find this paper with this title on arXiv already. So the theorem is this. So Pn is equivalent to a product of simplices if and only if for any vertex x of Pn, the intersection of all facets not containing x is non-empty. So at each vertex, you find then you find all the facets that not containing x, and see if whether they share a face or not. So this just means this. It means because it's simple. Then if the intersection of all the facets not containing x is non-empty, then they must share a face. And dually, if we state this in terms of the dual simplicial sphere, then it means that for any for any n-1 dimensional simplex sigma Kpn, the full simplicial subcomplex K Vk minus V sigma is a simplex. So this notation means the restriction of the simplicial complex. K. I mean, in this case, the Kpn, the restriction of Kpn to the subsets, the full subcomplex of this one. So let me give you an example. So what does that mean? So for example, so this is a product of two-dimensional simplex and one-dimensional simplex. So say for this vertex x, there are three facets containing x, but there are two other facets not containing x, right? So this one in the front, and then this one on the bottom, and then they share a face, right? So this is a face they share. So there's F1 and F2, they share face. And also you can check all other vertices. Those facets not containing the vertex actually share a face. And dually we can check this. So if you write down the dual simplicial sphere, so this is a two-dimensional simplicial sphere, and then say sigma is a two-dimensional simplex. It's a maximal simplex. And if you remove the vertex set of sigma from the vertex set of K, then what you got, the full simplicial subcomplex on these two vertices is just simplex, right? So these two statements actually are equivalent. So this is another criteria I found during I thinking about the proof of this one, but later I found that actually this one is simpler than this one even, and because you see for a high-dimensional simple polytope, there are much more two-dimensional faces than number of facets. So if you really want to write a computer algorithm to judge whether a simple polytope is equivalent to a product simplices, using this it's much faster than this one. Yeah, because this one you have to check many two-dimensional faces, but this one you see the number of facets there, very few, right? Very few.
So then the proof you are using the doubling of this one?
No. This proof is just using induction. It's quite independent. But to prove this one, basically it means that this property can be inherited by the facets of the polytope. Then by iterate argument, we can show that. So if the dimension is 2, then this property implies it is square or a triangle. Then using this, it implies it's a product of simplices. Right. I mean, this property. I mean, basically, the argument is like, we can do the induction, and if n is 2, then this property implies it's square and a triangle, And for arbitrary dimension, this property can be inherited by n minus one dimensional thing. Okay. Okay, so this is our contribution to this problem. So this is combinatorial side. Okay, I finished half. So how many times do I have? Okay, so the series topology. Huh?
15 minutes more.
15.
15 minutes more.
Topological conditions. I think I may need extra minutes. So the topological conditions.
So when you like Y and M, who is M?
M is where M?
Your theorem.
Your
Your theorem. I believe Y is you, but who is M?
I'm my students. I think I already said it's.
But he was outside.
Okay. And the second part is the topological conditions. So yeah, I think in this room probably people have already known the definition of Mohm-Nangle manifolds and the real Mohm-Nangle manifolds. So I won't repeat it. So Pn. So we can. So this is a real Mohm-Nangle manifolds, and this is Mohm-Nangle manifolds. Okay, so I just write the symbol. I think you know the meaning of this thing. And so this is a theorem. Yeah, actually this theorem is just exercise in Buchstaber's book. I think he wrote an exercise in his book. But when I write it, I didn't realize that. But Professor Julou told me it's just exercise in his book. So this is not so difficult. So Pn is equivalent to product simplicity if and only for some field k, the sum of the Beatty numbers of Zp with coefficient k, and the Beatty number means the dimension of this homology group. So with k coefficient, the sum is m minus n, where m is the number of facets of Pn.
Some field.
For some field, as long as there is a field k, and this holds, then it must be product simplices. So any field is okay. Summation of all the Beatty numbers with k coefficient is 2 to the m minus n. Then and also we can state this in terms of the Mohm-Nangle manifolds. So for some field k, the sum of the Zp and k is 2 to the m minus n. I think the proof is like this. Here the proof, we can use this doubling construction. It says because we know Rz Zp, so this is realized by Yuri Ustinovsky. He realized that we can actually write Zpn as the real Mohm-Nangle manifolds of Lpn. So to prove this one, actually, it's among to prove this one. And to prove this one, the argument is like this. So we can show that this property actually can be inherited by all the facets of Pn. And then by iterating this, we can show that if Pn satisfies this property, then any two faces of Pn also satisfy this two property. But for two-dimensional polytope, we know the real Mohm-Nangle manifold. So for square, we know that Rpn is S2, right? So this RZP. And the square, it gives torus, right? So we know, so we can check. And for others, for other two-dimensional simple polytope, this doesn't hold. So for this property hold, then all the two-dimensional face also satisfy this, and then it forces it to be either square or triangle. Then by the formal criteria, we can say it is isomorphic to product simplices. The argument is like this, also by the induction. So this property can be inherited by the faces. Okay. So this is a topological criteria from the Toric topology. And the third one, I think the third one, the third part is the geometrical conditions. And there's a theorem. So I first stated the theorem by Wimler. Theorem by Wimler, IEME 2015. So in the same paper as I just mentioned, so he proved that if Pn is equivalent to a product of simplices, if and only if there exists a quasi-toric manifold M2n over P such that M2n admits Tn invariant or S1n invariant non-negatively curved Riemannian metric. So he stated this condition in terms of the Riemannian metric, but it's called invariant non-negatively curved Riemannian metric. Okay. The quasi-toric manifold, you can think of it as is some very special quotient of a moment angle manifold. Okay, so this is. And now I state our condition. There are many similar statements you can make in terms of the curvature of some Riemannian metric on the space. So our theorem is this. Okay, this one is. So it says. So we can. We can also formulate some condition in terms of the real moment angle manifolds. So Pn is equivalent to a product of simplices if and only if there exists a non-negatively curved Riemannian metric on RZP, the real moment angle manifold, that is invariant under the Z2M action. Yeah, where M is the number of facets of Pn. Okay. The proof is. I think the proof has similar taste. As before. So if we have such kind of invariant Riemannian metric on the real moment angle manifold, then it means that for any phase f in Pn, suppose we have this pi, then pi inverse f. Pi inverse f is a collection of disjoint union of codimension 1 submanifolds in the real moment angle manifold. So by a very classical result in Riemannian geometry, if we have such kind of metric, then it means that pi inverse f is each component of pi inverse f is a totally geodesic submanifold of RZP, and then we can also show that it also have this kind of metric on each component of this codimension 1 submanifold. then we can iterate this argument to show that this condition also holds for any two-dimensional faces. And for two-dimensional faces, you know, so this is S2, this is T2, and so on. And by Gauss-Bonnet, we know that if such kind of metric exists on two-dimensional manifold, then the manifold must be S2 or T2. It cannot be any other faces, surfaces. Okay, and then by the formal criteria, we know it's isomorphic to product simplices. So this is another one. This is not hard either. Okay. So how many more minutes do you have? 5. Okay. I don't know whether I can finish in 5 minutes. Okay. But this kind of metric, so when I study this kind of problem, I mean, I feel this kind of metric is quite strong and not so natural. And from the information of the polytope, this kind of metric is just very man-made. It's man-made metric. And actually, I found that there's a very natural thing arising from the simple convex polytope, the Euclidean space, which is called quotient metric on real moment angle manifolds. Yeah, because we know that the real moment angle manifolds can be think of. I can use some gluing construction to construct this manifold. M is the number of facets. So it means that we can glue 2 to the m copies of Pn along their facets and then get RZPn. If you use a characteristic function, it just means that you can assign some color to each of the facets, and all the colors are just form a basis of Z2m. And we know that each Pn, if we consider it as a subset of Rn, then it itself is a metric space, right? We can define the distance of any 2 points in this space. Because it's convex, then the distance of any 2 points would be just the length of the straight line between these 2 points. So Pn is a metric space. A metric space means, I think everybody should know what's the definition of metric space. A metric space, okay, so write down the definition because I will use it. A metric space is a set X with a metric D. D is just some function such that for the distance of any 2 points is greater than 0 if x is not to y and dxx is 0, and it's symmetric, and it satisfies the triangle inequality. Okay, so this is the definition of metric spaces. And a metric space is complete if any Cauchy sequence in it has a limit. So this is the usual definition. So for this polytope, it is very natural that to consider it as a metric space, and the real moment angle manifold is just gluing of this 2 to the m copies of metric spaces, and we know there's a definition of, say, quotient space. So if we have a collection of metric space, we can form a quotient metric space. So this is a standard way to do that. The quotient metric space. So the definition is a little long. Say suppose we have. Suppose this is a metric space, and so let this to be an equivalence relation. Relation. Yeah, because we can think of gluing as the the cosets of some equivalent relation on a set. So let this be an equivalent relation. And we can first define the quotient semi-metric dr is defined as this. So drxy. So this is defined on the quotient space. So it's the infimum of sigma I equals E1 to K D Pi Qi P1 is x and the Qk is y. So the first point is x, the last point is y, k in n, where the infimum is taken all the choices of where the infimum is taken over all choices of pi, the sequence pi and qi, so that qi is equivalent to pi plus 1. Okay. So it means that we have some points, right? So a collection of points. So say P1, P2, blah blah blah, and Q1, Q2, P1, Q2. Q1, P2, Q2, something like this. And these 2 points are equivalent, and the P1 is just x, and PK, QK is y. Okay, and then we measure the sequence, and we measure the distance. So we add the distance of these 2 points and these points, right? And these two are, the neighboring, the Qi and the I plus 1 are considered equivalent. So in the quotient space, we take all this sequence and then take the sum of the infimum of the sum of the distance of these pair of points, and then it defines a semi-metric. We call it semi-metric is because sometimes 2 different points in the quotient space may have distance 0, 2 different points. So if we identify all the points with 0 distance, so if we identify points with 0 distance, we get an authentic quotient, a metric space. We get a authentic metric space. We denote it by this dr. Yeah. So this is so it defines a metric on the quotient space. Okay. So we just said that the real moment angle manifold can be defined as the 2 to the m copies of the quotient space of 2 to the m copies of Pn, and then we glue them along their facets, so we get it. So from this definition, then Rpn get a quotient metric, right? Quotient metric from. Do you have any questions? Sorry. RZPN. Get some quotient metric. It's very natural. Get some quotient metric from Pn. M. But this metric, I'm going to warn you that this metric actually depends on the shape of Pn. Depend on the shape. So for example, so we have this. So we have these 2 simple polytopes, and they're of course they're equivalent combinatorially, but they are not. If we glue them according to the rule, and then we get two quotient metric on RZ square. And then these two metric are not isometric in the geometric sense. They're not, because locally, I mean, the angle, actually, the angle of this polytope affects the geometry locally. So although they give the homeomorphic spaces, but the metric we got by this quotient procedure give you different metric eventually. Okay. So and then I want to define what's the meaning of non-negative curvature and the non-positive curvature for metric space, because in Riemannian geometry we have the notion of non-negative curve in terms of the scalar curvature, but here, not scalar, the sectional curvature. So, but here we want to build some similar notion for abstract metric space. So non-negative curvature, or non-positive curvature for, say, for length space. Well, here there is some subtlety because for any metric space we can induce a length space. So I think it's so. The more strict speaking, we define this curvature for length space. So it means that we can measure the. So we can define the geodesic between points. So in the length space. So what's the meaning of non-negative curvature and non-positive curvature in this setting? Because in the abstract metric space, we do not have like differential structure and smooth structure and the tangent space. I mean, and this kind of abstract metric space could be very abstract. But we do have this between points. We can define geodesic. I mean, the shortest distance. The curve is shortest distance. So say suppose we have three points, right? So we can connect them by some geodesic. The curve is shortest length. So this is a triangle. Here are triangle in the abstract metric space or length space. So it means that we connect these points by some curves which has a minimum length. Then for each triangle in X, then we construct a triangle A bar, B bar, C bar in the Euclidean plane. The R2 means Euclidean plane with the same length, with the same edge length. It means AB. The length of the length of the curve between AB equals the length of A bar, B bar, and BC equals B bar, C bar. And AC is A bar, C bar. Okay. So for this one, and then we can define, and because this satisfies the triangle inequality, right? So as long as it has some kind of this property, we can build a similar. So this is in X, and then we draw something similar in a Euclidean plane. So this is A, B, C. This is A bar, B bar, C bar. And they have the same edge length. And then we can compare their interior angles. And then sometimes the interior angle could be, smaller than this one. Sometimes it could be bigger. So it depends on the the property of the metric space. So the definition is so it is called non-negative. It's called to have non-negative curvature. Non-negative curvature if for any x, any x has a neighborhood, has a open neighborhood. Ux, so that every triangle in ABC in this open set if we draw the comparison, so this triangle on the plane is called comparison triangle, even only if the corresponding angle, interior angle of this angle and this triangle is greater or equal to the corresponding comparison triangle. So roughly speaking, it just says this metric space is non-negatively curved if locally it is a neighborhood such that all the triangle in this neighborhood looks thinner than the triangles on the plane, right? Or looks, yeah, it looks fatter. It looks fatter. It's nothing. So something like this. It looks fatter. The angle, this angle is greater than the corresponding angle on the plane. So this makes sense for arbitrary, like metric space with the length, right? So, huh? Oh, okay. So I will write down our theorem. Okay. I'm very glad I reached this point. So if we reverse this, and if we reverse this inequality, then it defines a non-positively curved. So on a non-positive curved situation, the triangle would be thinner than the usual triangle in the plane. So the theorem is this. So Pn is equivalent to the product of simplices if and only if the original Pn is just defined by the convex hull of some points. So the shape may not be so good. But if and only if we can somehow find another one, exist another P prime. So this is another simple convex polytope in the Euclidean space equivalent to P such that RZ P prime dP prime is of non-negative curvature, has non-negative curvature. Non-negative curvature. And as a metric space, it has non-negative curvature. Yeah, because this metric is kind of natural. We can build it from this polytope, right? So we can define this very naturally. We don't need to define extra smooth structure or anything else. A tangent space, a Riemannian metric. Okay, and another one is I think is more interesting. It says there exists. Another one is very geometric. It exists a P prime equivalent to P. The P prime is another simple convex polytope, so that all the dihedral angles, all the dihedral angles of P prime less or equal to pi over 2. So it means that if a simple convex polytope, so you can somehow deform the facets of the polytope such that all the dihedral, the dihedral angle. So it means so this is the dihedral angle of two facets, right? If all the dihedral angle of these two facets are all less or equal to pi over 2, then it must be a product of simplices. So you can, and this is a very simple geometric condition, right? So if we can deform, the P prime is equivalent to P, it means we can somehow deform the facets of the polytope such that all the dihedral angles do not exceed pi over 2, then it's product simplices. For example, so let's see the two-dimensional case. At least actually the proof is like this. This condition implies this, and this one will imply that every facet inherits this property, and then eventually, if all the two-dimensional face have this property, two-dimensional face, it means the polygon, right? So the polygon have this property must be triangle or square. Because if for other polygon on the plane, you know that for other polygon, you know Euclidean polygon, it means some interior angle must be greater than pi over 2. Only triangle and square can have this property. Now the dihedral angle is the interior angle of a triangle. Only these two can have or angle less or equal to pi over 2. And then use the formal criteria, we can say it is equivalent to that. So the idea is this. So if you glue, suppose the angle, if the angle is greater than pi over 2, then if you glue them together, then locally around this point, you will see that the quotient metric actually, if you draw the triangle on the corresponding triangle on the plane, then this one will be thinner. Will be thinner than this one. Will be thinner. You can see, because here now in the quotient metric, the points. So this is x and this is y. The geodesic would be like this, right? So in the quotient metric. So as long as there's an angle with, interior angle over, more than pi over 2, then it will create something. I think it violates the non-negativity. So the curvature condition. So this is the reason why why this implies it must be this and this. Okay. What is my talk?